Okay, so I will talk about just initial definitions of graphs and some simple mathematical tools of how to deal with graphs. And of course, this is an old, very old science started by Leonhard Euler in basically 18th century with a famous problem of 7 bridges in Königsberg. And since then, of course, a lot of things have been done. And so let's just start. And we will pay some attention to biological graphs, which appear in biology, because I think you are all related to biology. And there will be absolutely nothing about machine learning in my talk, because you know, I was doing my research without machine learning before it was invented, and but of course the concepts of graph are very important in machine learning, because the neural network is just one of examples of a network. So basically the main tool of machine learning is the central part of the graph theory. Yeah, so basically, beginning of my talk will be just taken from this wonderful book, Networks, an Introduction by Newman. So I really recommend you to get this book, and you can even get the PDF for free. And so it's a nice book to know. So there are, of course, lots of examples of networks, and all of them, so some of them are kind of real network, which is made by wires. So the links in these networks are wires, say, connecting computers, which is, for example, internet. And there are some networks which are not embedded in space, but it's a kind of logical networks. Like, for example, the connection between pages in the in the World Wide Web. And of course, like you can imagine a network of citations between the papers. So one paper, 2 papers are linked by a directed link if one paper cites the other paper. So, and you can see already that some of these networks can be not directed, but some of them can be directed, because, for example, in citation, it's clear that one paper is just cited by the other. So they are not in equal relation. One of the very interesting examples and most important probably example of a network is a power grid. It's again a real network made of power lines connecting power stations. So another thing is some, again, imaginary networks, like, for example, a friendship network. So each person is a node in this network, and the link is a friendship. And the very nice example of biological network is a metabolite network. Metabolite is a small molecule which, like sugar, for example, which react with many other molecules, and sometimes the reaction have several reactants and several products, and so basically a node in such a, there are 2 types of nodes in this network. One is a reaction and another is a metabolite. So it's an example of so-called bipartite networks, which we will talk about how to represent them in mathematical form. So, and of course, there is this neural networks, and they exist really in our brain, and machine learning is just trying to mimic the work of our brain by making all these networks in silicon, so to say. And basically, of course, in the neural network, which is used in computers, the network, the lines of this network is not real, but kind of modeled by software. And there are also ecological networks, like, for example, food chain networks, so many examples. Like a genetic regulatory network, which is very important of how our cells function, and a network of protein interactions, because protein form complexes with each other and act not alone, but in some groups. So you can see it's very many applications in different, in totally different fields. So so how to formalize the network is to kind of build an adjacency matrix for a network. So, for example, on this side you can see a network, right? And then if there is a link connecting nodes 1 and 2, then you see you put 1 in the first column and in the second row. And because this is a not directed network, you put symmetrically 2 to 1, because basically the node 2 has a link to node 1. And you see this is called adjacency matrix. It's Aij, and it's symmetric. And if you want to find a degree of a node, how many links emanating from a certain node, you have to just sum up the values in each column or in each row, because the matrix is symmetric. And then the degree, of course, the average degree is just basically one over, you have to sum up all these values that you get by summation in each column, and then you must average it divided by n, the total number of nodes. And basically C will be, of course, equal to 2m. M is the number of links. And because each link has 2 ends, then in this formula to get the average degree, you have the factor 2. And there is, of course, you can define this kind of density of the network, connectance density, because the total, the complete network would contain just n times n1 divided by 2 pairs, right? The number of pairs of a set of lengths n. So you see, usually people work with sparse networks. All the examples that I talked before is networks which are really sparse, where this density is going to 0, because you see n here in the n square, basically in the denominator here, and which is a square of number of nodes, and the number of links in the numerator. So this, when n goes to, when n is large, obviously this value goes to infinity very quickly, and density goes to 0. So we will talk mostly about sparse networks. And so this is a classical example of a network in which there are no self loops and no parallel links. But in reality, of course, there could be many situations where there are parallel links, and also links which are self-looped. You can imagine such networks as well. And then, of course, you have to modify this adjacency matrix. You have to put, for example, for a self-link, factor 2. So a number 2 for actually a link connecting a node with itself, and put it on the diagonal. And sometimes you need to put, for example, 3 for a node which is multiple. Yeah, so, and of course, there could be weighted networks, like, for example, power grid, because when you talk about power stations, right, so some pairs of power stations are connected by a power line. And these power lines could be of different power. So some may carry a big power, and another can carry a small power. And so basically, you can represent the original data is usually not presented as a adjacency matrix, because adjacency matrix takes a lot of space. Because imagine that if you have a million nodes, then you have a million square, which is a trillion. You have basically a trillion elements of the adjacency matrix, which is beyond the capability of any computer. So in reality, adjacency matrix is just a mathematical tool, but all the real calculations you are doing with, say, a list of lines or links or edges. So each line here represents an edge, and each line can be specified by the IDs of nodes to which it is connected. For example, this line 1 connects station 1 and station 2, and the power of this is 0.1, very weak connection. So you can construct, of course, an adjacency matrix, and you put on the proper places the weights. So it won't be just 1 or 0, but it will be a real number, which is the weight. Yes, so, and now we can talk also about directed graph. Like, for example, I say that the graph of citations is a directed one. So because one paper cites the other. So in these cases, mathematics is exactly the same, except that the adjacency matrix is not symmetric. So it can be asymmetric because, and moreover, there could be no two elements when you switch the indices of the on this matrix. You will never have the same node on basically on a symmetric. You will not have a one on a symmetric place, because only one paper can cite the other, and the other cannot cite the previous one. Only very rarely two papers which say come out in the same issue of the same journal, they can cite each other. So you see, you can actually construct a co-citation matrix, which will be a symmetric matrix out of this citation matrix. The co-citation matrix is just for each node, you determine how many papers are citing these two papers simultaneously. And from here, you may infer how closely related are these two papers. Because if many papers cite both of them, then it means that they belong to the same field. And then, of course, you can find how many these common papers which cite these two exist. And so you can construct a symmetric matrix C, which will be now this co-citation matrix, and it will be mathematically it will be a product of adjacency matrix times the transposed matrix. So, and the bibliographic coupling is just the opposite. So basically, instead of counting how many common papers are citing these two papers, then you can count how many common papers these papers are citing. So it's just the same combination, but you see, if here it's A times A transposed, here it's A transposed times A. And you can also compute this in degree and out degree using these matrices. So basically, the adjacency matrix and the linear algebra can determine some very nice properties of a network. And there are a lot of such properties. I won't talk about them in detail because I won't have any time. But you see, for example, if you want to find in the directed network a number of loops, then you can say that the necessary and sufficient condition for the network to be acyclic, so it won't have any loops, is that all the eigenvalues must be 0. So that's, of course, is very clear from this matrix because it's a triangular matrix with a diagonal which consists of all zeros, so all the eigenvalues must be 0. Yeah, so, and now we will talk about this hypergraphs and bipartite graphs. For example, you can imagine the network of actors, but not in terms of their personal friendships, but whether they were participating in the same movie. And then you can kind of link this to actors by a link. But of course, this link will be a kind of, you see, not really a link because it will involve many actors simultaneously. So instead of using these so-called hypergraphs, where you can have a link between, say, 10 different nodes, or between 15, you can present this by just a bipartite network, where there are two types of nodes. One type of node is an actor, another type of node is a movie, and then you connect the movies with actors. So then, again, formally, this becomes much more simple representation. So one of the very important biological examples of such a network is a metabolic network. So you can see that these circles are reactants, it's a metabolites. Okay, so for some reason, can you see my cursor? Yes. So you see this is the metabolites, and these are reactants. So these are the product of reaction. So for example, two molecules react, and they produce two other molecules which then go down along this metabolic pathway to participate in other reactions. And again, this is a bipartite network of different chemical reactions and different metabolites. And this is, in particular, this is a directed network because, for example, the example of actors and movies is a not directed network. And also, you can make a tripartite network because each reaction has usually have an enzyme which is works as a catalyst for this particular reaction. And so you see this triangles is a third kind of network, because in principle the same enzyme can help different reactions. So again, there could be many links from one reactant to this, from an enzyme to different reactions. Yeah, so another example of this bipartite networks is can be found in economics. For example, we published a paper about basically this banking crisis, which affect these so-called gypsy countries: Greece, Spain, Portugal, Italy, and how they were all connected with basically certain banks. And when the bonds start to fail, all these banks fail, and basically this, of course, affect the entire the cost of the bonds. And there was this terrible crisis where all these countries and banks were on the brink of bankruptcy. Yeah, so you see this is basically this formal relation between this hypergraph and the bipartite graph, and you can see that there is this, it can be described by a non-square matrix, because there are groups and particular nodes, and there are different number of nodes and groups. So and also you can, of course, from this bipartite network, you can easily produce just a network between the either nodes or the groups. Because the two groups will be connected if at least one node belongs to the same, both of these groups. So that's basically about bipartite graphs. And then there are, of course, graphs can differ by their topology. So many graphs, and especially it's easy to deal with such graphs, are the tree-like graphs. So in the tree-like graph, obviously there is this well-defined relation, which is where m, the number of links, is equal to just n minus 1, the number of bonds, the number of nodes. And also very nice property of the networks is just that you can determine a distance among two players or two elements of this network by just counting the shortest path on the graph between these two elements. And this shortest path is scales like logarithm of the number of nodes, because if on the small scale, this any network which is sparse, for which this density rho is very small, you can locally, they're basically trees, because there is a very small probability that the two neighbors of the same node will be again linked. This property actually is called clustering coefficients. Clustering coefficient, the probability of the two neighbors of a single node to have a link between them, themselves. So this is a very known quantity, but again, I don't have time to discuss all of this. So another very important property which determine mathematics of this network and their large-scale properties is the degree distribution. So basically, you just count how many nodes have degree 0, how many nodes have degree 1, 2, and you just find the fraction of such nodes, and you determine this histogram of degrees of each node. And so, of course, now people have a large collection of data. So now is basically a century of a big data. So we know, so we can construct so many different networks with thousands and sometimes even millions of nodes. So then, this our big data is basically all about networks, because almost any system you can represent as some elements and some interactions between the elements, which can be represented as links. So, and you can find the distribution of degree distribution of these networks. And you see, before this big data came, the most simple model of a big graph was a random graph, which was studied by Erdős and Rényi. And so this is a very simple model in which you just have m links, and you have n nodes, and you just randomly throw in these links between the two, between a pair of nodes. So, of course, this is a typical Poisson process, and when you imagine like you have a square divided in by a grid in many little squares, and then you throw m points in this big square, and then you count how many nodes are in each small square. So this is a problem from combinatorics, and the answer for this is a Poisson distribution, which is given by this very beautiful formula. So the probability to find a degree, a particular degree, is equal to the average degree to the k's power divided by k factorial, and there is a normalization factor e to the minus c, because the sum of this p of k's by definition must be equal to 1. So then you see, this is a Poisson distribution. It has a particular variance, and this variance is very small. It's basically all localized in the vicinity of this average degree c. And you can prove it with the help of generating functions. Generating function is a very useful tool for studying distributions. So basically, it's just an artificial construct, so that the probabilities will serve as a Taylor coefficients of a certain function. So you just multiply p of k to x to the k, and very simple algebra tells you that the result will be just exponent of x minus 1 times c. And then you see, you can differentiate this g twice, and then you will see by differentiation each factor in this x in each term of this network, you will see that this becomes just an average of k squared minus k minus average. So it's an elementary algebra, and so then you can actually very easily compute what is the standard deviation, which is a k squared minus k. So basically, this is a mistake. So k square average minus k square, is equal to C, and so it means that the sigma is just a square root of C. So this become a very small, because square root, of course, grows much slower than the average itself. It means that the distribution becomes a bell-shaped curve localized near this average. So, but all this was this is a beautiful and simple math, but it turns out that the real great big networks, which was studied in this era of computers, and when all this information can be easily studied, it turns out that the degree distribution is not Poisson at all for the majority of systems, and instead it's power law. So basically the probability of a big k is decreasing not exponentially like here, because factorial is decreasing very fast, faster than exponential. But it decreases as k to the some power, where gamma experimentally becomes some value between 2 and 3. And so these networks, of course, are totally different, because you can see that k-square average won't even exist for such networks, because basically this series will diverge for such a when you want to find the average degree, this series will diverge, and so such networks, because they don't have a standard deviation, such distributions, because they don't have a standard deviation, are called scale-free distributions, SF distributions, and basically they become very popular after this work of Laszlo Barabasi, who was the first to discover this fact. But of course, the fact that many different entities in nature or in society is distributed in a power law was known long before. And actually it was studied in economics by Simon. Actually Herbert Simon, the famous economist. So here are just the graphs of how the Poisson distribution look like and how this scale-free distribution look like. And the scale-free distribution has a very heavy tail. If you compare this graph, you see the tail for the Poisson degree is very kind of narrow, very decreasing very fast. But here you can see it's decreasing very slowly. And moreover, if you represent this as a double log plot, so you put just a logarithmic scale on the y-axis and the logarithmic scale on the x-axis, you can see that the histogram becomes approximately a straight line. And the slope of this line is nothing but the power of this distribution. And also you can study, instead of the distribution itself, the histogram itself, you can study a cumulative distribution, which is basically the sum or an integral of the nodes from the infinity to a given value. So basically it tells you how many nodes have a degree larger than certain degree, the fraction of nodes with big degrees. And this also decreases as a power law, but with a different exponent. So here the exponent, instead of original exponent alpha, becomes alpha minus 1. So the slope decreases by 1. But still, this graph is much smoother, because there is no this noise for the large nodes, and it's monotonically decreasing. So sometimes it's much more useful to study cumulative distributions instead of just normal, simple distributions. And you see, this is the example of this networks for www. And of course, www is a directed network because it's a network of basically references between different pages and the internet. And so you can see that it's look like Power law, and the slope here is quite close to 1 on these graphs. You can see that here is actually 6 decades, here it's 5 decades, so it's very close to 1, maybe a little bit larger than 1 in this particular case. So why this is so? Actually, it can be explained by this proportional growth model by Simon. And the first person who noticed these regularities was Ziff, a professor of Harvard University, who actually studied the sizes of cities. And so what he did, he just takes the statistical data from different American cities and put them in this graph. So on the vertical axis of this graph is a population of a city, and on the horizontal axis of this, oh, sorry. Oh, no. I kind of, yeah. Yeah, exactly. I'm sorry. I'm talking about the graph which I didn't show. So now you see you plot the population of a city, the population versus rank. And you can see a kind of a hyperbolic plot. On the top of this is a biggest city in the United States, which is in New York. On the second place is Los Angeles, which roughly have half the size of New York. Then there is Chicago on the third place, which has a roughly population of 1/3 of New York, and so on and so forth. And you can see a hyperbola. And actually, if you plot this, so now you can also basically present this rank versus population. Basically, just switch this graph, switch the axis of this graph, because the rank divided by n is nothing but the probability that a certain company, the certain city is larger than a given value. So basically, of course, you have again a hyperbolic plot, and if you plot any of these graphs in a logarithmic scale, you will see an approximately straight line with an exponent, Ziff exponent zeta, which is usually is very close to 1. So, and moreover, so basically the rank is approximately inverse proportional to the city size, and the rank is nothing but a cumulative probability distribution of size of the city. So you can actually very easily imagine how this Ziff plot appears, because you can have a very simple model of formation of these cities. So you can assume the kind of a minimalistic model of this process, which has just 2 factors. One is that each population of each city grow in time, and we assume that the growth rate of each city is the same, but also that with a very small probability, a person who is born in this particular city can form another city, kind of entrepreneur or a traveler, some kind of a great person can create a new city in a totally different place. And so you see, kind of schematically, this can be represented in such a way that you see there was a kind of a big city, then a new person form a new city, but then certain time pass and the first city grows by a certain factor. This newly formed city grows by the same factor, and a new city was formed. So now there is a 3 cities with different populations, and then you can see that the size of the city is roughly proportional to the basically the population of a city is proportional to so the rank of the city is proportional to the time when it was when the city was created, because the biggest city was created as at a very long time ago, and the smallest city, which has a basically very big, very small rank, was created not so long time ago. And also, of course, the population of the city which was created at a certain time t is basically is inverse proportional to this time, and thus the two properties, rank and size, can be related by a very simple formula that rank is inverse proportional, population is inverse proportional to rank. So this is a very elementary model which works pretty well. And not only cities are distributed in this power law, but also, for example, people like billionaires. So if you make the same ZIF plot of billionaires, you can see that it's also approximately a straight line on a double logarithmic scale. And you can also, of course, so this rank was just so wealth versus rank, and here is rank versus wealth, which is a cumulative distribution. And also what is amazing is not only that these billionaires are distributed in such a way, but also the words in any language. So for example, if you take in Italian the Bible and Harry Potter translated in Italian, and then you can actually basically put the words in the order of their frequency. So at the beginning, of course, the most frequent words are just kind of articles. Like, for example, in the English language, the most popular word is Z, and the second most popular is A. Then what is interesting that on approximately 10th place, there is a main character of this book. For example, in the Bible, it's Signore, the Lord, and on the Harry Potter, it's Harry. So it's appear roughly on sometimes 10th place or so. And then again, if you plot the graph of each word against its frequency, you can see something which looks like a power law on a double logarithmic place. Of course, it's not a perfect power law, but still have the same property. Of course, here it's not really a proportional growth when you have this frequency of words. So it's more difficult to explain it with this simplistic model, but still it's an interesting fact. So basically we just slightly generalize this the previous model, and we basically introduce these parameters, particular parameters of which tells you the probability of creation of a new city, the probability of creation of a new the birth of a new person, lambda, and the probability of death of a person, mu. And then we can, or basically it can be not necessarily cities, but it can be firms. the same thing, so that the firms may consist of certain units, and each time the new firm can be created with some probability, and also a new unit inside the firm can be created. So then you have this 3 parameters, nu, lambda, and mu, which describe this proportional growth model. And then after some very little algebra, more or less of the same sort that I demonstrated before, you have a very nice formula for this distribution P of k, which basically becomes just k inverse proportional to k square plus b, where b is a correction which is basically nu divided by lambda minus mu. Then you can easily understand why Barabasi found this exponent about 3 in his model of internet, in his data for the internet. Because you see, his model was the following, that you see, at the beginning there was just one provider of the internet. When the second provider of the internet, so where is the cursor? Yes, when the second provider of the internet appears, of course, it wants to connect to already existing one, so that it can connect to more people. And then again, a new node is formed, and it wants to select among these two the biggest one. And then this process is connected, so each time a new provider is created, it's tried to connect to the node with the largest degree. And so it means that now in the space of these degrees, you have the same preferential growth model. And here, of course, for each new node, you have one extra connection in the degrees of the previous nodes. So it means that lambda, the growth of the growth rate of the each node is proportional to the speed of creation of the new nodes. Nu is equal to lambda, and here mu, the death rate, is equal to 0. So this formula gives you just b equal to 1 divided by 1. So it's just inverse proportional to k to the third power. And now we will talk about, go back to graphs again, and then we will study this disconnected components of a network and their distributions, which is a very important point too. So there is this very nice theory which is called percolation theory, which studies this kind of transition. So when the number of links between nodes decreases, there is a certain critical point in which the giant component to which the majority of nodes belong it disappears, and only small clusters remain. So this is a very nice model of phase transitions in physics, and it's related to other phase transitions, like transitions from liquid to gas, or transition between ferromagnetic and paramagnetic. So it comes from physics. But actually, very simple calculations can show you how this giant component depends on the average degree. And so basically, if you kill more and more links from a given node, then the degree of this network, of course, will decrease, and the fraction of the nodes in the giant component decreases and becomes 0, actually exactly when the average degree is equal to 1. This is, of course, correct only for the Erdős-Rényi graphs, the simplest one, where the generating function is just an exponent. But of course, this theory can be generalized also to any graph with any distribution. Of course, if this graph is random. So what is given is just a degree distribution, but the number of, so each node in the beginning is assigned certain degree with certain number of stubs coming out of this node. And then you select one node and start to connect it to different stubs. You selecting these stubs totally at random. In such a way, you create a random network. And actually, of course, in this process of creation, you can see that the probability that node will be connected to a certain stub is proportional to the degree of this node. And there are only k-1 links coming out of this process. So this is becomes like a branching process. And again, there is very little probability that these branches will be connected. And then there is a very simple way of create this function, generating function h of this branching process, which is the probability of a node times k, because you have this extra factor k to be connected to this node, times k, of course, k-1, because it's only k-1 links coming out of this node. And you have to normalize this by dividing by the average degree. And the average degree is, of course, just the derivative of original generating function computed at 1. Then you can actually, now we will talk even about more simple model, which is a Cayley tree, where all this mass is very simple. You can see that this is the Cayley tree with a degree z equal to 3. So you can see that each node has exactly 3 links connecting it to its neighbors. Then, of course, if you take some nodes with probability 1 minus p out, right, then the distribution will become a new distribution. Not all the nodes will have a degree z, but some of them will have a degree 2 with such a binomial probability. And with degree 1 with this probability, this is just a simple binomial formula. And of course, with probability 1 minus p to the third, all the neighbors will be killed, and so the degree of such a node will be 0. So you can compute, of course, this degree distribution of such a kind of decimated network, and it will be px plus 1 minus p, because these binomials sum up with x to this nice little formulas. And then you can compute all these degrees. And moreover, you see, you can define this probability that a given link is going to a giant component, which is 1 minus p plus p times f squared. Because if you select a certain link, right, and you ask you what is the probability that this will lead to will not lead to a giant component, right? So first of all, it won't lead to a giant component if the first node is dead, like for example here. But then also, if this node is not dead, then you have to look what will be the probability of the giant component for these two links not to go to a giant component. And and of course, the probability that both of these links will not go to giant component is proportional to the square of the probability of each of these facts. So then the simple recursive formula for this probability to not belong to the giant component is just given by this quadratic equation. So this quadratic equation can be easily solved, and then you can graphically solve it, and you can see that there is always one solution which is equal to 1, and then there is a if p here is greater than 1/2, then you will have extra solutions which correspond to the existing actually giant components. Because if f equal to 1, it means that the probability not to belong to giant component is 1, and so you definitely, the giant component doesn't exist. And so this is the condition here, is that the slope of this curve, which is a right-hand side, right? At the point at point 1 should be greater than 1, because the right-hand side for this formula is just this straight line. And so the probability, the critical probability for this percolation problem is just equal to the slope of this function 1 minus pf square in this particular case. And of course, because when you differentiate it here, it becomes pf times 2. So it means that p should be greater than 1/2, in order to have a giant component. So percolation here exists at p equal to 1/2. Above p equal to 1/2, the giant component exists. Below, it doesn't exist. And so, of course, very similarly, you can find the distribution of this giant components. So here we are not computing the distribution of giant components themselves, but the distribution of sizes of the branch by which you go from a certain link. And again, generating function gives you the way of very nice and simple calculations, basically, because the summation of this type of summation, when you compute how many, what is the size of the sum of these two clusters, which are kind of branches or sub-branches of this big branch, given by this formula, and then when you multiply it by x to the s, very simple algebra gives you this very simple formula for the generating function of this distribution of the component sizes. And then you can solve it, this equation. Now it will depend on the parameter x, and now you can expand it by Taylor expansion near x equal to 0, and you have such a very simple formula, and you can see that the probability decreases inverse proportionally to the n to this 3/2. And because actually here we just select a given random link, but in a network, of course, there are many such links, and the probability that this link will belong to a cluster of size s will be s times bigger than the probability that it will belong to a small cluster. So that's why the probability of the clusters in the big network goes like inverse proportionally to the 5/2. So this is just any percolations, in any percolation transition in this kind of randomly connected graphs. This is a very famous law that the distribution of clusters is also a power law, and it goes inverse proportionally to power 5/2. So now you see we will talk about very little time. I think I already kind of over the time, unfortunately, but I want to talk about the work which was done by Nikolai Dokhalyan and Shakhnovich, Professor Shakhnovich, in which they study the faults of different proteins. And so they wanted to basically solve the question of either evolution is convergent or divergent. So if basically the convergent evolution is just kind of a Darwinian idea that only the faults which are kind of stable will be will remain, and all the rest will be killed by Darwinian selection. So in this case, you would expect that the distribution of these different faults will be like a Poisson distribution with some fixed value, and basically the distribution of the degree distribution of these links between similar proteins will be also described by Poisson. But on the other hand, there could be a model of divergent distribution, which is again this model of proportional growth. With some small probability, a new gene can be duplicated, and so now you have two genes for the same protein. And one of these, and because now you have two genes for the same protein, now it's easier for this another protein, which is a kind of not really very important, can mutate and mutate more or less at random, and so it can create more interesting faults, and so in this way the evolution will diverge, and more different faults will be created. And so basically they constructed a matrix of all different proteins, and the links between these two proteins is just the z-score in terms of their structural similarity. And of course, this will be a complete graph with many, basically n times n minus 1 divided by 2 links, and this will be completely untractable. So what they did, they just decimate this graph by just preserving the links which have a similarity score greater than certain z mean equal to the 9. And this point was actually the percolation transition of this system. And of course, not surprisingly, you have clusters in this network which are distributed in a power law with this exponent 5/2. So this is not the main discovery, because this is actually a trivial fact. Near the percolation transition, all the nodes, except maybe some very strange and regular, will have this distribution of clusters, whether going in the power law to the minus 5/2. But what they found is a power law of degrees of the surviving links at this particular z. And this power law was 1.6. So you can see that all these degree distributions are approximately straight line on a log-log paper, and there have this degree distribution of 1.6, which is kind of close to 2 again. So you can imagine that the process which leads to such a distribution is some sort of a proportional growth, which I described in the beginning, so that sometimes a new protein, a new gene can be created by duplication, and then it starts to mutate and diverge from its parent, so to say. Okay, so you can see that this is actually the graph theory can be very nicely used in biology, and of course it's a basis of machine learning, because the deep learning networks are just these neural networks. Okay, thank you for your attention. I'm sorry that it took me more time than I promised, so it's always my problem, you see. It's my problem for 50 years. Okay.
Very much, Sergey. So,
okay.